Let's take a look at two more examples of how to find the work required to lift liquid out of a particular container. This container in the drawing here is basically a box. It's a rectangular parallelepiped, which is just another name for a box. The bottom is the rectangle and the sides are at 90-degree angles. This is sort of like a swimming pool that is in Olympic shape. We want to know how much work is required to move the bottom 1 meter of water out of the pool using a pipe that extends 2 meters above the top edge of the pool. The pool is originally 4 meters deep. The pipe extends another 2 meters. So the bottom layer of water is between 5 and 6 meters below where it needs to go. The depth of the water is originally 3 meters. The swimming pool is 10 meters by 15 meters by 4 meters deep. Now, how are we going to compute the work required to move the bottom 1 meter of water out of this pool? Our formula in words is work is the integral from the lowest layer of water to be moved to the highest layer of water to be moved, times the density of the liquid, times gravity, times the volume of the layer that needs to be moved, times the distance each layer moves. Let's set it up. In order to compute it, first we need to know what is the volume of one layer. If you look in the picture, you can see I've drawn sort of the outline of one tiny little layer of water. Think of this layer like a sheet of paper. Mostly two-dimensional, but with this tiny little thickness to it. That tiny thickness is again the differential. If I set my origin to be at the bottom of the pool, anywhere around the pool, it won't matter, then the differential is again going to be dy. So in this case, the volume of the layer of water to be moved is the area of that little layer, like a sheet of paper, 10 meters times 15 meters, times the thickness of the layer, which is the differential dy. That gives us 150 square meters times dy. In order to complete the integral, we need to know what distance does that layer of water need to move to get out of the pool and to go out the pipe that extends 2 meters above the pool. So what is the distance each layer of water moves? Originally, the pool is 4 meters tall and the pipe extends another 2 meters. That's 6 meters above the bottom of the pool. But each layer already is at a particular height and the height is y. So the distance that each layer of water needs to move is 6 meters minus y. Now let's set up the actual integral. I need to go from the lowest layer of water to be moved to the highest layer, and the directions to the problem say move the bottom 1 meter of water. The bottom 1 meter of water extends from the origin up to 1 meter. So my limits of integration should be from 0 meters to 1 meters. That's the water layers I'm moving out. Then I need to multiply by the density of water and gravitational force. Those are constants, so I can go ahead and move them out of the integral. They will not affect it. The volume of the layer is 150 square meters dy. So I can put in 150 meters squared with the differential dy. And then I need to multiply by the distance that each layer of water moves, which I computed to be 6 meters minus y. You'll notice that this problem is quite a bit easier than the one in the first video when our tank was a conical shape. The reason is this is a regular solid, so the volume of each layer is actually a constant other than the differential. So I can now compute this by distributing the 150 meters squared, or I could opt to pull the 150 meters squared out of the integral since it is a constant. I'm going to do the latter. So I will have 150 meters squared, rho times gravity, density times gravity, and then I just need to integrate the 6 meters minus y. This will give me 6 meters times y minus y squared divided by 2, which needs to be evaluated between 0 meters and 1 meter. When I plug in these values, I will again have 150 meters squared rho g times 6 meters times 1 meter minus 1 meter quantity squared divided by 2 minus 6 meters times 0 meters, which of course will just be 0, minus 0 meters quantity squared divided by 2, which will also of course just be 0. When I complete the arithmetic, I end up with 150 meters squared rho g times 6 meters times 1 meter is 6 square meters minus 1 meter squared is 1 square meter divided by 2 is going to be 1/2 of a square meter. And 6 meters squared minus 1/2 square meter would be 11/2 meters squared. When I multiply this by what I have over here, I should end up with the following: 825 square meters rho g. Now to complete the problem, I need to make sure that these units did work and that I got joules since I'm in the metric system. Now rho for water is again going to be 1,000 kilograms per meter cubed, and we're going to use 9.81 for our gravitational constant, 9.81 meters divided by seconds squared. I have meters cubed on bottom, and I have, let's see, what do I have on top? Meters cubed, which lets me know there's something wrong. I should be getting kilogram meters per second squared, so I'm going to go back and check my units. Look above here. I have meters squared times meters squared. That should give me meters to the fourth. So I'm going to change my units here to meters to the fourth, and that makes these units here also meters to the fourth. And now I have meters to the fourth times meters, which is meters to the fifth, divided by meters cubed would give me meters squared. So I am going to have meters squared on top with a kilogram and per second squared. Kilogram meter squared per second squared, that is a joule. So my units worked. All I need to do now is compute the number. If you take 825 and you multiply by 9.81 and then by 1,000, you should come up with 8,093,250 joules. And that's how you would compute how to find the work required to move the bottom 1 meter of water out of the tank. Now, if I wanted to move the top 1 meter of water out of the tank, it should take less work because the top meter of water has less far to go. Let's take a look at another example. In this example, instead of having a rectangular parallelepiped or a box, or having a right circular cone, this time we have a cylinder. How much work is required to move all the water out of the tank using a pipe that extends 5 meters above the tank? The tank is originally 22 meters tall. It has a radius of 14 meters. The water is at a depth of 12 meters, and the pipe extends 5 meters above the top of the tank so that it is 27 meters off the bottom. I'm going to choose to put my origin in the center of the bottom of the tank so that my y-axis is extending down through the center of the tank, and I can use this as the y. Now, what would a sliver of water look like? If I'm moving all the water out, then basically what I have is a tiny little sliver right here that looks like this. and again it goes around. It is again a disc shape, and the differential for that little layer of water is again going to be dy. So now how do I set up the formula? My formula is work is the integral from the low layer of water to be moved to the high layer of water to be moved, the height of the water to be moved, times rho, the density of the liquid, times g, gravitational force, times the volume of each layer to be moved, times the distance each layer moves. In this case, when I'm setting up the work, my lowest layer, since I'm moving all the water out, is going to be from 0 meters to the top of where the water is, but the water only goes up to 12. Do not integrate to 22. There's no water between 12 meters and 22 meters. There's nothing to move. So you only work across the layers of water for the limits of integration. Then I have rho g, which are constants. And what would the volume be? Similar to the right circular cone, this makes a basic coin shape or a disc, where the volume would be the area of the cross section, which is going to be a circle, so pi r squared times the depth. In this case, when we're looking at the volume of the layer, it's going to be pi r squared dy. Is the radius of each layer different from the radius of the tank? Because the tank is a right circular cylinder, the answer is no. The radius of every layer of water is also 14 meters. So that would give me that the volume of each layer is 196 square meters pi dy. Again, it is a constant other than the differential. I can choose to leave this as a constant and pull it out when I pull out the rho and g. I'll slide the differential to the end, and now I need to know what distance does each layer of water need to move. Water has to come out the pipe, which is at a height of 27 meters off the origin. So it has to move from where it currently is up to the top of the pipe. It currently is at height of y, from the bottom of the tank to its current height. So the distance it moves is 27 meters minus y. This sets up this problem to find the work required to move all the water out of the tank. From here, it's a simple matter of completing the definite integral. I'll work it out and then show you the result. After we've set up the problem, we can go ahead and start to solve it. I pulled this and the rho g out of the integral as they were constants. That left me 27 meters minus y to integrate as the integrand. That gives you 27 meters y minus y squared over 2 to be evaluated between 0 meters and 12 meters. For the next step, moving down, I plugged in the 12 meters and the 0 meters. 0 meters, of course, results in 0. When I multiply out the numbers here, I end up with 324 square meters minus 72 square meters. That gives me 252 square meters in the next line, which I need to multiply by the other values. At this point, since I'm one step away from the end, I went ahead and plugged in the value of the density of water, 1,000 kilograms per meter cubed, the value of gravity on Earth, 9.81 meters per second squared, and multiplied. When I was done, I got this value, and try not to forget to include the pi. When you're done, note that your units do work out. I have kilograms on top, 1, 2, 3, 4, 5 meters on top, divided by meters cubed gives me meters squared. That's kilograms meters squared over second squared, which is joules. This is the end of the second video.